Hello guys, in this lecture I will go over simulating the dynamics of multi-degrees of freedom robots such as this 3 degrees of freedom robot which is called a PUMA robot or the PUMA configuration, which is basically have your first axis which is mainly rotation about the z-axis, and then you have the remaining 2 degrees of freedom on this robot. Here we're gonna ignore basically the rest dynamics. So what we will do to be able to simulate the dynamics here, what we are going to do is we will first begin by capturing the potential energy in the system and also capturing the kinetic energy of the system. And then we will use Lagrange, and then we find the angular acceleration on all these joints. And from the angular accelerations, we can obtain angular velocities. And then by numerical integration, we can find the angular positions on each of these joints. And then that way we can have actually a realistic physics-based dynamic model of the system. So I think everything is going to be simple here in terms of finding the potential energy of the system. It's very easy. So we'll simply locate the center of gravity of the various links. And we know the potential energy will be equal to mgh. Next step is we need to find the kinetic energy of the system. And each rigid body will actually have two kinetic energies, right? It will have a translational kinetic energy, or 1/2 m multiplied by the velocity of the center of gravity squared, right? So these are easy. And then you have 1/2 I omega squared. All right, so it turned out that expressing the potential energy is very simple, because if we are using the DH transformations or any other transformations, we can always find the position at any point. Basically, we can put a frame on the center of gravity, right? And we can find the coordinate of that frame, and then we can find the z elevation of that frame. So whatever that frame is, we can easily capture that, right? And then we've already did an exercise on that. Likewise, it's very easy to find that the translational kinetic energy. So what I'll do is here, let me do something simple. Okay, all right. So my kinetic energy will be converted into two things, right? So we have translational, and then we have rotational, right? And let me, okay, so these are our, oops. Okay, so kinetic energy basically has two components, translational and rotational. Translational is easy. Why? Because from the x, y, z positions of the center of gravity, we can use a chain rule of differentiation, right? We know, for example, x is a multivariable function of θ1, θ2, θ3. You could have actually 6 joints, right? You can do all that chain rule. You can find x prime, you can find y prime, and then you can also find z prime. So it's easy. What is actually complicated here is, maybe you can guess it, is the rotational kinetic energy, which is for 1 degree of freedom, it's 1/2 I omega squared, right? And you only have rotational energy if your rigid body actually have some dimensions, right? As a result of I, I is equal to mr squared, for example, for a point mass, right? If r is 0, then your moment of inertia is 0, then your rotational kinetic energy is 0, right? So we're gonna try to find how we can actually find the rotational energy, for example, of link 3. How can I find this rotational kinetic energy? And then, this guy could be rotating in all weird directions, right? It's being rotated by this guy, then it could be rotating about itself, or even more like link 6, right? So it's very arbitrary manipulation. And we need to find the rotational kinetic energy of any joint on the robot. And once we actually do that, then the whole problem becomes simple. Well, luckily, there is actually an easy way of actually doing that. And then I will show you how we can do this. All right, so let's focus now on finding the rotational energy, rotational kinetic energy of every link. What we will do is, we know that every link will have ultimately one angular velocity vector, correct? So if I start with link 1, I know that omega 1 in frame 0 is going to be like this, right? And mainly, we know it from the z vectors, right? So the z is the axis of actuation. It actually defines the direction of my velocity. But more importantly here, when we have a serial manipulator, we know that the velocities are actually adding up, right? Especially, for example, in θ2 and θ3, right? These velocities are are basically adding up because the velocities are relative, correct? So here's what we can do. We can actually write the following in a very simple manner, right? So I know omega 1, 0 is the angular velocity of the first link, and I don't really care in what direction it is. If it's rotational, right, then it actually has this omega 1. It has a vector, right? And then here I'm putting it as random, but it has to be expressed in terms of the base frame, right? I cannot express omega 1, 0 in frame 2 or frame 3. Simply, the magnitude is not going to change, but how we express the vector will actually change. So it's very important that when we add these vectors, they have to be added in the same frame, like here, omega 0, right? Frame 0. So if I want to find the total angular velocity of link 3, right? What I will do is I'm actually going to have to add them up, right? It's omega 1, 0 plus omega 2, 0 plus omega 3, 0, where omega 1 is the relative angular velocity, right? Only omega 1 is actually absolute because we know x0 is fixed. But omega 2, 0 is not absolute. Omega 2, 0 is rotating about z1, but I know that z1 will actually rotate, right? So I have to actually convert z1 into my base frame, right? And then z2 and then z3, right? But in general, so every rigid body will have an angular velocity vector, right? And it could be arbitrary, right? So what we will do is we're gonna add for every link, we're gonna make it to be absolute. So here's the one on link 3, here's one on link 2. So simply adding omega 1 plus omega 2. So this is the angular velocity vector on link 2. And the angular velocity vector it doesn't actually have a reference frame, right? I mean, it does actually have a. Okay, so these are our angular velocity vectors as rigid bodies. So what we'll do is we do know also that because of the DH convention, we know that the angular velocities or rotational vectors, right, are always along the z0, along the z-axis, right? So for example, I know that z0 actually drives link 1, correct? And then z1 drives link 2 and Z3 drives link 4 in that case, right? So here that should be Z2, right? So Z2 will actually drive link 3. We know that. Why? Because, for example, I have, the first link, which is here basically, is rotated about the ground, right? By Z0. So Z0 has to be fixed. And then you rotate the second link about the first link. So it's about Z1, correct? This is how the DH convention works. So what we can do actually, if you do this, literally, you can actually find the total angular velocity vector on link 3, right, in the base frame. And you actually, what is omega 1? Omega 1 is nothing but theta 1 prime, right? Omega 2 is nothing but theta 2 prime, and then omega 3 is nothing but theta 3 prime. By adding all these, you will actually have this omega 3 0. It will have an x component, y component, and then a z component. So we'll actually have some, random angular velocity vector on that link. So you could have, as many degrees of freedom that you want, and this will actually always apply and it will always work. Okay, if a joint is a translational joint, it doesn't add an angular, doesn't actually result in so let's say, joint 2 is actually a translational. So in that case, you don't actually have rotational components. So you don't actually have an angular velocity component as a result of that, but you do actually have it as a result of some other joints which are rotating it. All right, so if it was a translational, so you get the point, so you don't basically add that contribution. Okay, so we're good here. What I would like to do, so right now I actually have, I would have a link, right? And I know that I have this angular velocity vector. But how can I actually get the kinetic energy of it? Well, I know the rotational kinetic energy is equal to 1 over 2I omega square, right? And what is I? Basically, you have to basically map or project the angular velocity vector on the frame of the link, right? Whatever frame that you have. And that way you will actually be able to align this vector with the frame. And then, if it was like a linear link, the I will be, for example, ml squared over 12 and, and along about for an axis that is perpendicular to the link. So for the two axes which are perpendicular to the link, for example, if it was linear, I know the moment of inertia is going to be ml squared over ml squared over 12, and then along the actual link, right, assuming it has no dimensions, that would be 0. You could also choose to actually get that from SolidWorks, and then you can also do that as well. You can get the moment of inertia from SolidWorks. But what is important to do here is actually we need to so this is, by the way, how we get the z vector. So you already know how to do that. You know, if you have an H transformation, was it DH or any homogeneous transformation, we know our z vectors are located in our homogeneous matrix, right, which is the third column. And we'll use that basically here, right, to do this. And I'm going to continue here. And all right, so what I would like to do is, let's say on link 3, I'm trying to find the kinetic energy of link 3. So what I would like to do, so the vector is not going to change, but I would like to be able to view this vector from a frame that is on the link. And that way I can see, you know, what is a component of this angular velocity vector, which is perpendicular to it. What is the component of the angular velocity vector, which is along the link, because this component will actually create no kinetic energy, assuming the link is slender, and etc. So how do we do that? Simply, we can actually use a transpose, right? Well, I know omega 03 is equal to R03 multiplied by omega 33, correct? So I'll use simply the inverse of that. The beauty here is you already have all your transformations. So to basically map the angular velocity vector, all you do is basically you're simply doing that projection, which we have actually learned before. If you use a rotation transformation, it will actually only map the component. So how would you view the component of this vector from this frame into another frame, right? So if you do that, you can actually get this omega 33. And to look into more detail, so this is what you actually end up with, right? So my total kinetic energy, let's say on link 3. So this is frame 3. Omega 3, this vector is not going to change, right? So that vector is always there, but you know how I view it will actually change this index. So if I put 3 here, basically I'm viewing this vector in this frame. And you know, we can actually get the x3, y3, z3, and then whatever moment of inertia I have along the z-axis will multiply omega z. Whatever moment of inertia along the x, basically you're gonna get what? You're gonna multiply it by omega 3x. So this is basically your total rotational kinetic energy. You do that, basically you can capture the full rotational dynamics of the system, and then you can actually continue on and then do the rest. You can actually do it like that. You don't really need to do this. So most likely in SolidWorks, you can actually just provide your moment of inertia about your principal axis. So you'll basically ignore the rest, and then you'll actually simply have x, ix, iy, and then iz, right? If these were your principal axes. All right. Okay, great. So when you do that, basically the this matrix equation applies. So you can actually put your moment of inertia as a matrix, ix, iy, iz. If you actually do this, it's like you are basically doing the equation that I showed you earlier, right? So this guy is equivalent to this guy. All right, so this is the rotational kinetic energy of your link 3. Just some basic rotational matrix, inertia matrices of basic geometries. If you have a slender bar, for example, you end up with this. If it was a circle, obviously it's symmetric about all the axes. And then if it was a cylinder, basically you're going to use this, where h is the height of the cylinder, r is the radius of the cylinder. All right. So you can use those to kind of estimate the dynamics you can estimate basically the moment of inertia of the robot, right? Initially, if you don't actually have a SolidWorks model, you can assume, okay, so that link looks more like a, you know, like a rectangular block, right? Or maybe this robot will have a link that actually looks like a cylinder, right? Or you can simply do it in SolidWorks, put the, you know, the weight, the geometry, densities, etc., and then you can actually capture that, or you can request it from the manufacturer. All right, guys, so that is really it regarding the PUMA robots. And really the most important takeaway here is that, you know, how you actually handle that. And then I want to come back to my initial code, basically how we did that. So literally you start by defining the position of your center of gravities, right? And we can get the linear velocities of the center of gravities, which is obtained using the chain rule of differentiation. What we're adding here basically is simply we're adding this rotational component, right? And the way we will actually get the rotational component is it's going to be done using, like I said, this equation, right? Or mainly this, right? Theta 1 prime. So we still actually have omega. The zero we have it from our homogeneous transformation. We have these. We find the kinetic energy based on this guy, right? And then we actually add this rotational kinetic energy on all the links. We add it where? We add it to our kinetic energy, right? Which is right here, right? So we know this is my kinetic energy. Right now it's only translational. Well, actually, here we actually did incorporate one of the rotational components. Here we were dealing before with a planar robot, as you remember, so we don't actually have the other two components. But when you have a PUMA type robot, you have a yaw on the first axis, then you will actually end up with some weird rotations on the other axis. So you would actually need to incorporate that. So this is fine if you are not considering, if you're not considering, like rotational about the base axis. But to be able to consider that, to be able to consider robots with articulated arms or articulated wrists, right, where you have perpendicular axes of rotations, and you would actually need to do that. And that is it, guys, regarding PUMA robots.